Welcome to Quality Code. Today we'll be taking a look at the word search problem. And so you're basically given a word, in this case A, B, C, C, E, D, and a board of characters. And your job is to construct this word from the given board. So in this particular example, we can construct A, B, C, C, E, D by first selecting this A, and then B, C, then going down to C, and then E and D. Something to keep in mind is you can only choose characters adjacently. So in the case of A, you can't choose F since it's not adjacent. And you can't use the same character twice. So for example, you can't go to A and then to B and then back to A. So the solution to this question is pretty much a brute force solution. So what we're going to do is select every single character and perform a depth first search to try and find the given word. So let's take a look at the code. So we're given the exist function that returns a boolean, and that takes in the board and the given word. The first thing is we initialize all the information that we've got so far. So the number of rows, the number of columns, the board, and the word. Next, we loop through all the characters in the board, and we try to perform a depth first search, starting at that particular row and column. If we're able to find the word, starting at that character, then we return true. Otherwise, once we've looped over the full board and we haven't found anything, we simply return false. So let's take a look at the DFS function now. So as previously seen, it takes a row, column, and index. Index is essentially representing the current index inside of the word that we're trying to match. So in this case, we check if B of RC is equal to the word at that particular index. If it is, then we've essentially matched that character. And so next we check if that index is equal to length minus 1, meaning we've matched all the characters. If that is the case, we return true and we're done. Otherwise, we cache the value at BRC and we change the value at BRC to be equal to 1. So in this particular case, 1 essentially means we visited that node before, and so there is no need to go back there. And the reason this works is our board only contains the characters from A to Z. And next we calculate the new possible indices which we could go to. And to do that, we have two directional arrays. And just to clarify that, so in this case we have RD, which is representing the possible row directions, and CD, the possible column directions. And so in this particular case, 1, 0 would essentially mean down, -1, 0 is up, 0, 1 is right, and 0, -1 is left. So we calculate our new indices. We make sure these indices are valid. And if they are valid, then we perform depth first search recursively at our new indices. And of course, index +1, since we've just matched index. And if this is true, we return and we're done. If we're unable to find the word from this particular node, then we need to backtrack and reset the value at BRC. The reason for this is, let's say the word was EEC. Then let's say we started the depth first search at E. Then this would be 1, and then this would also become 1. But we would never find the C from this particular node. And so if we don't reset them to their previous values, then we would never be able to find a word starting from E, since this would already be 1. So that's the solution to this problem. We loop through every single character inside of the board, perform a depth first search, and if we find the word, we return true, otherwise we return false. For space complexity, in the worst case, our depth first search recursion stack finds the word, and that would use up O word of length in terms of space. And for time complexity, at each point inside of the board, we have 4 directions in which we can go, give or take. So we have 4 to the power of word length multiplied by n times m, since we repeat the depth first search process for every single character inside of our board.